The P versus NP problem is one of the most famous and challenging open questions in the field of computer science. It's so significant that it's one of the 7 Millennium Prize problems selected by the Clay Mathematics Institute, carrying a $1 million reward for whoever can provide a correct solution. In this presentation, we'll cover 3 key things about this topic. We'll talk about what exactly is the P versus NP problem, what P and NP stand for, and the implications of this problem and where we are today. So, to start, what exactly is the P versus NP problem? The P versus NP problem was first introduced by Stephen Cook in his 1971 paper, The Complexity of Theorem Proving Procedures. This paper would serve as the theoretical backbone for classifying problems based on their solvability and efficiency, launching the field of complexity theory. At its core, the paper poses a fundamental question. If a solution to a problem can be verified quickly, can a solution also be found quickly? To understand this, we need to look at 2 major classes of problems this question deals with, being P, which includes problems that can be solved efficiently in polynomial time, and NP, which includes problems whose solutions can be verified efficiently in polynomial time, even if we don't know how to solve them quickly. Beginning with the first class of problems, P, which are those that can be solved in polynomial time. Polynomial time refers to the amount of time an algorithm takes to solve a problem, where the number of steps required is bounded by a polynomial function of the input size. This means the time it takes to determine whether a solution exists for a problem with n inputs can be expressed as a polynomial function, where a variable such as the input size n is raised to a fixed power such as 2. Some examples of problems in the class P include sorting algorithms such as bubble sort with a time complexity of n squared, and merge sort with a time complexity of n log n in the worst cases. Search algorithms such as linear search with a linear runtime complexity, and binary search which runs in logarithmic time. And finally, some graph algorithms such as Dijkstra's algorithm, where a basic implementation runs in quadratic time, and breadth first search, which runs in n plus k time, where n is the number of nodes and k is the number of edges. Each of these algorithms run in polynomial time or less, which means they're solvable efficiently and fall within the class P. To summarize, problems in P are those that can be both solved and verified using a deterministic algorithm, that is, an algorithm that always follows the same sequence of steps and produces the same output for a given input within polynomial time or less. Now, moving on to the second class of problems, which are those that can be solved in non-deterministic polynomial time, also known as NP. These are problems where a solution can be verified quickly, even if we don't yet know how to solve them efficiently. That is to say, if we were given a problem P and a proposed solution S, we can verify that S is correct in polynomial time or less. However, there is currently no known algorithm that solves P in polynomial time. Because there is currently no known polynomial time algorithm that solves NP problems, we don't know whether such an algorithm truly exists. The time complexity for solving these problems could range anywhere from linear to factorial runtime, varying with each problem and its approach. To study these problems, computer scientists use a non-deterministic algorithm, a theoretical model that can guess a correct solution and then verify it in polynomial time. If we were given access to such a theoretical algorithm, we wouldn't know how it found the answer, but we could verify that the solution is correct using a regular deterministic algorithm and do so in polynomial time. A classic example of an NP problem is Sudoku. What makes Sudoku an NP problem is that if we were given a completed Sudoku board of size n, we can easily verify whether it's correct. This can be done either by hand or using a deterministic algorithm in polynomial time by checking that every row and every column contains the numbers 1 through n with no duplicates. However, while verifying a solution is easy, there is currently no known algorithm that can reliably solve any Sudoku puzzle in polynomial time. The best existing algorithms, like backtracking, can solve many puzzles efficiently, but in the worst case, the runtime grows exponentially with the number of empty cells. Now that we covered both categories of problems, let's talk about what it would mean if P equals NP. Everything we've discussed so far falls under the class called NP, which stands for non-deterministic polynomial time. These are problems where a solution can be verified quickly, specifically in polynomial time, even if we don't know how to solve them efficiently. Within NP, we have our subset of problems called P. These are the problems that we can both solve and verify in polynomial time using a deterministic algorithm. And then we have the subset called NP-complete. These are the hardest problems in NP, which we currently have no known polynomial time algorithm to solve, but whose solutions can be verified in polynomial time. Now, if we were to find an algorithm that solves even one NP-complete problem in polynomial time, that would mean we could solve all NP problems in polynomial time. And because NP-complete problems are the hardest problems in NP, showing that they can be solved as efficiently as problems in P would mean that they are no harder than P problems, showing that there is no real difference between the two classes. This could prove that P does equal NP, and all NP problems would fall under the class P. Of course, the opposite could also be true. It's entirely possible that no polynomial time algorithm exists for solving NP-complete problems. If that's the case, then P and NP-complete would remain separate categories, both part of NP, but fundamentally different in how hard they are to solve. In this scenario, we would conclude that P does not equal NP, meaning there are problems that we can verify quickly but cannot solve efficiently. This would confirm that some problems are just inherently hard, and no amount of clever algorithm design could make them fast to solve. Now, why would solving just one NP-complete problem mean we can solve all the others? To understand that, we need to look at the very first NP-complete problem, the Boolean satisfiability problem, or SAT for short. This problem was introduced in Stephen Cook's 1971 paper mentioned earlier, the same one that launched the entire discussion around P versus NP. So what exactly is the Boolean satisfiability problem, or SAT? SAT asks a very specific question. Given a Boolean formula using variables, ands, ors, and nots, is there some way to assign true or false values to the variables so that the entire formula evaluates to true? In simpler terms, we're trying to figure out if the formula can be made true by choosing the right combination of truth values for its variables. An example like this seems simple, but as the number of inputs grows, so does the time complexity to solve it. Regardless of the algorithm used, the SAT problem has exponential time complexity in the worst case. That means the time it takes to solve a SAT instance can grow exponentially with the number of variables, something like 2 to the n, where n is the number of variables in the formula. So far, no algorithm is known that can solve all SAT instances in polynomial time. Even the most advanced SAT solvers, used in real-world applications, still face this exponential growth for certain types of inputs. This is part of what makes SAT such an important and challenging problem in computer science, and why it's central to the P versus NP question. But why would finding a polynomial time algorithm for SAT let us solve other NP problems too? Well, in the same paper by Stephen Cook, he showed that every problem in NP can be reduced to SAT in polynomial time. That means if we take any NP problem like Sudoku for example, we can convert it into an equivalent SAT problem using only AND, OR, and NOT logic. So if we had an efficient algorithm that could solve SAT, we could use it to solve the converted version of Sudoku and then just translate the SAT solution back into a Sudoku solution. This logic doesn't just apply to Sudoku, it applies to every problem in NP. That's why solving SAT in polynomial time would effectively give us a way to solve all NP problems efficiently. So what would happen if it turns out that P does equal NP? It would mean that many problems we've long considered hard to solve are actually easy to compute. We just haven't found the right algorithms yet. This would include problems like route optimization, like the traveling salesman problem, puzzle solving, like Sudoku or crosswords, and protein folding in biology. All of these would become efficiently solvable, but this breakthrough would also come with some consequences. Modern encryption standards like RSA and elliptic curve cryptography rely on the assumption that certain problems are hard to solve in polynomial time, such as factoring large numbers or computing discrete logarithms. If P did equal NP, and someone finds a fast enough algorithm for those underlying problems, much of our digital security would be broken, including secure messaging, online banking, and blockchain systems. In short, P equaling NP would change how we fundamentally think about certain problems. On the other hand, what if P does not equal NP? That would mean there really are problems out there that we can verify quickly but can't solve efficiently no matter how clever we get with our algorithms. In other words, some problems are just inherently hard to compute, and that boundary between easy and hard problems is real and unbreakable. This would confirm why we still rely on things like brute force, heuristics, and approximation algorithms to get by when solving NP problems in the real world. It would also mean that our current encryption standards remain safe, at least from classical algorithms, because the hard problems they rely on, like factoring and discrete logs, would stay difficult. Ultimately, if P did not equal NP, it reassures us that we understand the limits of computation, and those limits are not going away. So, where do we stand today on the P versus NP problem? Even after decades of research, the question remains unsolved. We still don't know whether P equals NP or not. This is why it remains one of the 7 Millennium Prize problems with a $1 million reward for a correct proof. So what do most computer scientists think? Most experts believe that P is not equal to P. They think it's unlikely that there's a fast algorithm out there for every NP problem. We just haven't proven it yet. But until we have a formal answer, the mystery of this question remains open.